Hi there, IB. Just want to do a quick overview of the first part of this next section on trigonometry, 10A and 10B, where we're looking at the sine function and graphing it all. In 10A in class, you probably already started to look at periodic behaviour. So in other words, what we do is we see some things keep repeating. And we had some graphs here that you could look at and see, yes, there's a pattern where the function is repeating. And you could look at it and think, well, decide how they differentiate between the range, the maximum minimum values, the period, how long it takes for the pattern to repeat, and the principal axis where it's oscillating around. So we want to have some way of describing these. We then went to the example where we had a Ferris wheel, where we had a point going, some cable car going round the Ferris wheel, and we can relate that to the unit circle. But first of all, you probably looked at someone on the Ferris wheel. In the Ferris wheel, we've got a 10-metre radius, and it's 2 metres above the ground. So if we look at it from two perspectives, the first perspective is the height. How high above this central position is the little carriage that the people are sitting in? And if we take our time zero at this normal position where we take our angle zero and plot the points for the height, we come up with this shaped curve. And because we were talking about the height, which is like the y-coordinate, we related that to the sine of the angle, because that was the y-coordinate of the point on a unit circle. We could have then looked at the distance from the centre. So we looked at and saw how far from the centre the little carriage was. So if you're imagining someone down here looking upwards, then the point starts off, or the carriage starts off on this side at plus 10, and as it moves up over the top, it's getting closer to the centre, then goes to the other side at minus 10, comes back to the centre. So we see the point, or the carriage, oscillating between these two values of plus and minus 10. And we saw that for the vertical perspective, the carriage was oscillating between plus 2 and plus 22 as it goes up and down. So for the horizontal one, we saw that oscillation. It's a funny sort of graph. It doesn't look like a function because of the way we've drawn it. So what we can do is consider this time as our independent variable. So we can just rotate that around so our independent variable is on that x-axis. So it's just a different way of drawing it. And let's bring our values for our x-axis down here. So there's the distance from the centre. We have time as our independent variable along the x-axis. And now it's a function again. And so we can see that this is related to the cosine of the angle. And in this case, we could write this function as d cos of t, where t is time, and that's because we can write it like that because the angle theta is directly related to the time. At a particular time, the little carriage is at a certain angle of rotation. So we could write this as the distance from the centre is a function of the angle or a function of time. The height is a function of time or a function of the angle. In 10B, we go on and look at this in a closer detail, and here's our point. We're now starting to draw this as a point on a circle. It's not the unit circle here because the radius is 10, because that was the radius of our Ferris wheel. But we can remember from SOHCAHTOA, from the sine rule, that theta is h over 10. So sine theta is h on 10. So the height is 10 times sine theta. So now this is another way that we can come up with that expression for the height as a function of theta. And how does that height vary? So we can now go on and plot this. So it's the same sort of concept, except this time let's take the unit circle. So we've got something generic that we can apply to any situation. And we want to plot what's the height of our point P, that's the y-coordinate, as our point moves around for different angles. So our sine function, we can look at it as y is sine theta, that's the y coordinate, or we could think of it as the height as a function of theta for our Ferris wheel, or height as a function of time for our Ferris wheel. If you plot the values using a calculator, either using your degrees or radians, and we get sine theta, so we get these values with your calculator, and plot them on your axes, this is the curve we get, so that's not surprising, it's the same shape curve. We see our period is 2 pi. So in other words, in terms of the y coordinate for our point, from going around here, we end up back at the same y position after one full rotation. It also makes sense that our maximum and our minimum are at plus and minus 1. So let's just write that in here. So our maximum value is going to be 1, and our minimum value is minus 1. So as the point goes up and around the circle, we're going around this way, then here's our maximum at 1 and our minimum at minus 1. The amplitude, how high is it going from the principal axis, is 1. Let's put our principal axis in. So take this line up, this can be our principal axis. We can see it's oscillating around that point down the line, in this case of y equals 0. So that's our oscillation, our principal axis. So I've done it with that pink line. Like any of these axes, we need to give an equation. So in this case, it's y equals 0 for the principal axis. The period, how long it takes to repeat, we saw it's in 2 pi, we get back to have the pattern repeat. Or if we're in degrees, then it's 360 degrees. We've only just taken this graph to 2 pi, but obviously because we're back at this position, it's going to start repeating itself. So this curve will continue to go up, reach a maximum at another pi on 2. It's not a very smooth curve, sorry about that. And it'll keep repeating that pattern. In class, you've probably started looking at that investigation. So here we wanted to see if we now want to start changing our graph and see how do we change it so it looks like the Ferris wheel in a real situation. We can put all these values in, our A, B, C, and D, and transform the basic curve y equals sine x into something that matches the situation. So you were looking at what effect did these values have on the maximum and minimum, on the amplitude, the principal axis, the period, the horizontal translation, and the vertical translation. So you should be working through that investigation, but we did a quick revision of Chapter 5 just to be able to also predict a little bit what's going to happen. Remember that if you multiply by a function by a constant sort of out the front of the function, that's the same as doing a vertical stretch by that scale factor of a. If you multiply the x's by a constant, in this case b, then that's the same as a horizontal stretch. And that's got a scale factor of 1 on b. So remember the difference there with the x direction. If you add a constant at the end, then that's the same as a vertical translation or a shift of those d units. Here, remember it's x minus c, that's the important one here. That's a shift of c units in the horizontal direction. The other ones we looked at, if you put a minus sign in front of the whole function, that flips it in the vertical direction. So that means it's around the x-axis. It's flipping up and down vertically, that direction. Whereas if you put the minus, if you have a minus in front of the x, it's a horizontal flip around the y-axis. So you're flipping it left to right instead of up and down. At this point, you should stop the video and make sure you've worked through these two investigations. There's three parts to it. So work through all those to see what patterns you observed. Having worked through that, you might be able to come up to some conclusions. What I want to run through here is this little applet, which you can access through your textbook as well, where we can see what's the effect that changing A, B, C, and D have on the sine function. So this shows our sine function. You can tell it's a sine function because it starts at the 0, our y coordinate, goes up to 1 and down and back again. This is done in radians because I can see that one whole cycle occurs and finishes just after that 6 value here, and remember that 2 pi is 6. So we're working in radians. So the first thing you did was, I'm not sure exactly the order, but let's look at A. Here's our A at the front. If we double that, we see what's happening. You should have observed in that investigation that our amplitude is increasing and our maximum and minimum are changing accordingly. Now our amplitude is 3, so it's going from +3 down to -3. Oh, it's 2.8. There's at 4, pardon me. So we've got an increased amplitude. If we now come down to smaller, 0, if we hit 0, we should get a flat line. Well, it's meant to be a flat line. If it's -1, see now how it starts at 0, but instead of going up, it's going down. And that's that vertical reflection in the x-axis. Same story at -2, amplitude's 2, but it's been reflected down. Back here to 1. Oh, put it on 1. All right, let's do the B value. So that's the horizontal stretch. So now let's see, as we make our number bigger, right, remember your scale factor for B is 1 over B. So our period here was 2 pi for one cycle. If I now multiply that by 2, so I get sine of 2x, see what's happened to our period? It now comes in at pi. So 2 pi times a half, 1 over 2, gives us pi. So when we have 2x, we're multiplying everything on the x-axis by a half and brings it all inwards towards the this y-axis. If I come over here and make it smaller, let's say it's at a half, let's try to get exactly half, 0.5x, so our B value is a half. That means our scale factor is 1 over a half, which is 2. So our period now goes for 2 pi. So we've only got half a cycle here. So here's one whole cycle from +2 pi to -2 pi. So altogether it's now 4 pi for one cycle. So that again shows us that our half now has doubled the period. What do you think happens if we make it negative? There's 0, our flat line. See now, it's, instead of going up, it's now going up this way. So it's actually a reflection around this way, even though it looks like it could be a reflection that direction. But we'll talk more about that later. So let's put that back on 1. On 1. Awesome. C is our horizontal shift. So note if I shift it to the right, so it's becoming plus, the shift C is 1, so it's x minus 1. Our whole curve is shifted 1 unit to the right. If our C is 2, we keep shifting it to the right, back to where it began, now shift it to the left. So note the plus 1.1 means a shift to the left of 1.1 units. And then our last one for D, up we go, goes up 1 unit, goes up 2. So here we now have, this is our principal axis, is at y equals 2. Our curve is oscillating around there. So if I want to have it up 2, we're going to shift it to the right 1. and we could do a vertical stretch of 2, or 3. So we can put all those together where we get a vertical stretch, horizontal shift, vertical shift. So can you just check that your summaries from your investigation are reflecting that? That's at 1. Let's leave that at 1. What do we want? A at 1, and we'll just bring that back. Anyway, I don't need to bring that back. So that should be your summary. So now what we want to do at the beginning of class, there's a quick summary. So this is the summary of the textbook. The amplitude A is affecting the amplitude. Note you'll often see that written as the absolute value because your amplitude is always a positive number. So that's your vertical stretch. B is that horizontal stretch, and that affects your period. So this is a very important relationship that you will often use. So because it's got the scale factor of 1 over B, the period becomes 2 pi times 1 on B. So in other words, it's 2 pi on B. If you rearrange that and you know the period and you're trying to find a B value, then you're just going to have B is equal to 2 pi over the period. Okay? And of course you can do this in degrees. So your period is equal to 360 degrees over B, etc. So always look carefully at the domain for your function. All right? This important one here, your translation, C, when it's minus C, it's that shift to the right. If it's plus C, it's a shift to the left. This notation here, remember from chapter 5, if it's translated by CD, C is in the X direction, the D is in the Y direction. So that means we've got a shift of 2 units to the left and up 3 units. So that's the summary. So you should maybe pause that and copy that down into your notes. It's a very important summary. So if we just quickly do this one, and then we'll look at the other ones in class. We want to graph this without using technology. We want a graph of minus 2 sine x from 0 to 2 pi. Whenever I do this, I just draw in my curve to start with because I find that easier. So there's my normal sine curve, and obviously it keeps going. So you could put little arrows to say it keeps going. If it's minus 2, the minus tells me, so let's go green. So the minus tells me there's been a vertical reflection or a vertical flip. All right, so that means it's now doing this. All right, I don't have any B values or anything there to change the period, so that means that my period still here is at 2 pi. All right, and that's pi. So there's no change to the period. I've had a vertical reflection. The last one here, I just need to shift this over a little, this circle. The last bit here to notice is the 2. So the 2 here tells me all my y values are being multiplied by 2. So it now comes, down here, sorry. So we're now down here, we've got double the amplitude. So that means I'm coming down here, up here, not the smoothest of curves, sorry, and keeps going. So this is now at minus 2, this is at plus 2. So we'll look at some more examples in class. So meanwhile, make sure that you've got that investigation done and that you're happy with what you've seen and that it matches that summary we've done. Thanks for listening. We'll see you in class. Bye for now.